Just before we start these reacting mass calculations on page 16, I want to remind you of our moles equations. So our triangle is mass on the top, then we have N and we have RFM. From that we can get three equations, and you get that by covering the subject of your equation, covering what you want to work out essentially. So if I want to work out my number of moles, I would cover that, so you can put your finger over that, and you would get mass over RFM. If I want to now work out my mass, I cover that, and I get that mass is equal to N times RFM. And if I wanted to work out my RFM, I would cover that, and I get that RFM is mass over N. Those are your three moles equations. We are going to be focusing mainly on these two. N equals mass over RFM, and mass equals N times RFM. So turn to page 16, we're going to be working from there. So now that we have worked on moles calculations, we're going to have a look at how we can apply these moles calculations to chemical reactions and what we can work out with that information. So we're working on page 16 of your booklet, and it has reacting masses at the top of the page. So what we need to have a think about first of all is what a chemical equation actually tells us. The reason that we have worked on balancing equations is because in a reaction, atoms are neither gained or lost in a chemical reaction. The atoms are just rearranged. And so we can read balance symbol equations quantitatively. That means we can get an idea of the quantity of the reactants and products involved in a given reaction. So let's have a look at this example, which is the combustion of magnesium, or when magnesium reacts with oxygen. And how we can read this equation is by the balancing numbers in front of each of the reactants and the products. We can read this equation as the fact that 2 moles of magnesium react with just 1 mole of oxygen, because there's no balancing number in front of the oxygen. So that's the equivalent of saying that there's a 1 in front of it. And when 2 moles of magnesium react with 1 mole of oxygen, they give 2 moles of magnesium. And that all comes from the balancing numbers in front of the formula. And what is really useful about this is that if we know the number of moles of one of our reactants or products, then we can work out the number of moles of any of the other reactants or products in an equation. So for example, if I was given the number of moles of magnesium in this reaction, I could work out how many moles of oxygen I needed to react with that number of moles of magnesium. And I could work out how many moles of magnesium oxide would be produced from that reaction. And actually, we can work from our mass as well. So if we were given a certain mass of magnesium, I could calculate the number of moles of magnesium by using the equation N equals mass over RFM. Then I could work out the number of moles of oxygen that I would need, or the number of moles of magnesium oxide that we produced. And if I wanted to work out the mass of either of those things, I could use my equation mass equals N times RFM. So we have a step-by-step process for this as well. And these are called reacting mass calculations. So the first thing we do in these calculations is we always write the equation. We need to make sure it is balanced. But at this level, you're generally given your equation for these calculations and asked to work from an equation. Then we want to write the information we've been given. So for example, whatever mass we are given underneath that part of the equation. We then calculate the number of moles for that part of the equation. That's really important because you can only transfer the number of moles from one part of the equation to another. You cannot transfer mass from one part to the other. Okay, then we bring it to the other part of the equation by multiplying by the stoichiometric ratio, or in other words, the balancing numbers ratio. You don't really need to worry about that big word, stoichiometric. It's just basically the balancing numbers ratio. And then we can convert back to mass by using the equation N equals mass times RFM. But this is best looked at by using an example, which we'll do on the next page. Let's start with worked example 1, which is the reaction of magnesium with hydrochloric acid, giving us magnesium chloride and hydrogen. And the most important thing to remember with these examples is not to move the masses. We have to only transfer moles from one part of the equation to the other. Once we've converted to moles, we can move it anywhere, to any other part of the equation. Okay, so let's read the question carefully. The question asks us to calculate the mass of magnesium chloride. Okay, so I've been asked to calculate the mass of magnesium chloride. So I find that in my equation. Magnesium chloride is MgCl2. And I put a question mark at that. That's what I've been asked. And it says it's from the reaction of 4.8 grams of magnesium with hydrochloric acid. So I have the mass of 4.8 grams of magnesium. So the first step is to write down everything you know underneath that part of the equation. So we've done that, and now we want to convert to moles. So the information I have is that I have 4.8 grams of magnesium, so I need to convert that to moles. So my moles equation is N equals mass over RFM. The mass of magnesium is my 4.8 grams. And the RFM of magnesium is just the relative atomic mass of magnesium, which is 24. If I divide 4.8 by 24, I get 0.2 moles. Now that I've converted that to moles, I could bring that to any other part of the equation. My hydrochloric acid, my magnesium chloride, or my hydrogen. But the question asks us to work out the mass of magnesium chloride. So I'm going to bring my number of moles over to the magnesium chloride. And I show that by drawing an arrow from the moles that I've just worked out over to my magnesium chloride. Now, step number 4 in your process of these reacting mass calculations is that you transfer the substance from one part of the equation to the other by multiplying by the stoichiometric ratio. And that's basically the balancing number ratio. So I have to ask myself, what balancing number do I have in front of Mg? And what balancing number do I have in front of magnesium chloride? There's no number in front of it, so that means our ratio is just 1 to 1. Where there's no number in front of a formula, you can take it as there being an imaginary 1 there. So our ratio is 1 to 1. That means that 1 mole of magnesium will react to give us 1 mole of magnesium chloride. So therefore, if I have 0.2 moles of magnesium, that means I'm going to produce 0.2 moles of magnesium chloride. The ratio is 1 to 1, so essentially I don't have to multiply it by anything. So now I have worked out that I'm going to produce 0.2 moles of magnesium chloride. But the question asks me to work out the mass of magnesium chloride. So I need to use my mass equation, mass equals N times RFM, to convert that number of moles of 0.2 into grams. I need to work out the RFM of magnesium chloride in order to do that. And perhaps we can work that out off to the side here. If you have room, write it down somewhere on your page. So the RFM of magnesium chloride is going to be equal to 1 times your mass of magnesium, which is 24, plus 2 times your mass of chlorine, which is 35.5. Put that into your calculator, you should get 24 plus 71, which is 95. So your RFM of magnesium chloride is 95. So putting it back into my equation, I'm doing mass is 0.2 times by 95. Putting that into your calculator now, you should get 19. And when I use my equation, my mass is always in the units of grams. So what I have just been able to do is, from the fact that I have 4.8 grams of magnesium, I've been able to work out how much magnesium chloride I would produce. From 4.8 grams of magnesium, I can produce 19 grams of magnesium chloride. But I had to first convert my mass of magnesium into moles, bring that over to the magnesium chloride, and then convert it back to mass by multiplying by the RFM of magnesium chloride. If you feel confident with that, pause the video now and try worked example 2. It would be good to give it a go before watching the video. So pause the video, try it now, even on a scrap piece of paper if you're not sure, and then you can replay the video to go through the example. Okay, so worked example 2 talks about calcium carbonate being heated to constant mass. You don't really need to worry about what that means. Essentially, it's you heat it until the mass doesn't change, and that's because you're going to be removing this carbon dioxide from the calcium carbonate molecule. So heating to constant mass just basically means that the reaction is over. So we can calculate our number of moles. So let's read through the question and write down the information that I know. It tells me that I start with 5 grams of calcium carbonate. So I want to write 5.0 grams underneath my calcium carbonate. It reacts to give me calcium oxide and carbon dioxide. The question asks me to work out the mass of calcium oxide. So I put a question mark underneath my calcium oxide and the units of grams, because that's the unit that mass is in, and that will remind me which part of the equation to bring my moles to. Okay, like any of these questions, I first of all need to convert my mass into number of moles. So I have calcium carbonate, want to convert it into number of moles, and I do that using my equation N equals mass over RFM. My mass is 5 grams, and my RFM of calcium carbonate is going to equal 1 times by my calcium mass, which is 40, plus the mass of carbon, which is 12, and plus the mass of 3 oxygens, oxygen each with a mass of 16. That gives us a total RFM of 100. Then when I'm working out my number of moles, I take my mass, which is 5 grams, and I divide it by 100. That gives me a number of moles of 0.05 moles. I then want to draw an arrow to the part of the equation that I want to work out. So I'm going from my 0.05 moles here up to my calcium oxide. I need to ask myself, what's the ratio here of my balancing numbers? Again, there's no balancing numbers in front of my calcium carbonate or my calcium oxide, so therefore my ratio is 1 to 1. So that means that 0.05 moles of calcium carbonate will give me 0.05 moles of calcium oxide. Now that I've got my number of moles of calcium oxide, I can convert that back to the mass of calcium oxide. So I use my equation, mass equals N times RFM. The RFM of calcium oxide I need to calculate. That's just the mass of calcium, which is 40, plus the mass of oxygen, which is 16, gives me an RFM of 56. So putting that back into the equation, I can do mass is 0.05 moles times by my RFM of 56, which gives me 2.8, and my units are always grams. Over now onto page 18 for the next example, worked example 3. And this is going to be an example where my stoichiometric ratio, or my balancing number ratio, is not 1 to 1. So there's a little bit of an extra step here. Okay, so we're told in this question that we have iron oxide, Fe2O3, or hematite is the name of the ore, is converted to iron and we're asked what mass of iron can be obtained from 16 tonnes of iron oxide. Now, the first thing to note here is that your mass must be in grams. So where we have 16 tonnes of iron oxide, we need to think about what that mass is in grams. Well, we looked at the fact that 1 tonne is 1,000 kilograms, so 16 tonnes is 16,000 kilograms. And 1 kilogram is 1,000 grams. So therefore, 16,000 kilograms is actually 16 million grams. Okay, so now I start my moles calculation as normal, and I write down the information that I have underneath the equation. So, the first part of the question asks me, what mass of iron? So that's the question. Iron is Fe, so I want to write my question mark underneath iron. What mass can be obtained from 16 tonnes of iron oxide? So I want to write 16 tonnes underneath my iron oxide, but I write that in grams, which is 16 million. So I have 16 million grams of iron oxide. First step, as always, convert that to the number of moles. So N equals mass over RFM. My mass is 16 million. My RFM I need to calculate. And you could do this off to the side. So your RFM is going to be 2 times your mass of iron, which is 56, plus 3 times your mass of oxygen, which is 16. And that's going to give you an RFM of 160. So for my moles calculation, I'm doing 16 million over 160, and that gives me 100,000 moles of iron oxide. Now that I've worked out my number of moles, I can bring that to any other part of the equation, but I need to consider my balancing number ratio at this point. So I want to bring it over to the number of moles of iron, but I need to think about my ratio. There's no number in front of my iron oxide, so I can take that as equal to a balancing number of 1. But there is a 2 in front of my iron, so my ratio is 1 to 2. What that means is that for every 1 mole of iron oxide, I produce 2 moles of iron. So essentially I produce twice as many moles of iron as I do as iron oxide. So what I need to do here is I need to multiply my number of moles of iron by 2, because I produce twice as many moles of iron as I do iron oxide. So my number of moles of iron that I'm going to produce is actually 200,000 moles. So I have to take into account my balancing number ratio. Now that I've got my moles, I can convert that back to mass. And I do that by using my equation, mass equals N times RFM. My number of moles is 200,000. My RFM of iron is 56. And I'm just taking the RFM of the formula. I don't take into account the fact that there's a 2 in front of that, because I've already taken that into consideration in my balancing number ratio. So I'm just looking at the RFM of what's in my formula, which is iron. 200,000 times 56 is 11,200,000 grams. That's a very big number. So what I can do is I can divide it by 1,000,000 to get it back into tonnes, and that would give me 11.2 tonnes. If you were to give your answer in grams, that would be fine, unless the answer specified or the question specified that you had to give it in tonnes, but that just tidies it off a little bit. Again, worked example 4 is very similar, so if you want, pause the video and have a go at that and then replay the video to check that you've got the right answer. But give question 4 a go, even if it's on a spare piece of paper, to see if you can do it. Okay, so this time we're reacting aluminium and oxygen. We can see we've been given the balance symbol equation. So first step, write down all the information we know. First thing we're given is that we have 27 kilograms of aluminium. I need to convert that to grams first of all. So I times by 1,000, 27 kilograms is 27,000 grams. That's of aluminium, so I write that down underneath my aluminium value. That's 27,000 grams. They are heated in a stream of oxygen until constant mass was achieved, basically until the reaction is over. Determine the mass of aluminium oxide formed. Aluminium oxide is Al2O3, so I'm trying to work out my aluminium oxide. Okay, as always, we start by working out the number of moles of the mass that we've been given. So we've been given the mass of aluminium, so I need to convert that to moles first of all. N equals mass over RFM. The mass is 27,000. The RFM of aluminium is 27. 27,000 divided by 27 is 1,000. Now that it's in moles, I can bring it to any part of the equation, but I want to bring it to the aluminium oxide. So I draw an arrow from my number of moles to the aluminium oxide, but I need to consider the balancing number ratios. You can see that my balancing numbers ratios is 4 to 2 in this case. So on my arrow, I write 4 to 2. There's a couple of different ways that you can do this step. The first way is by dividing by the number you're going from and multiplying by the number you're going to. So I can divide by 4 and times by 2. That's the first option. Or I can say to myself that a ratio of 4 to 2 is the same as saying a ratio of 2 to 1. 2 to 1 means that for every 2 moles of aluminium, I only form 1 mole of aluminium oxide. So essentially, I form half as many moles of aluminium oxide as I have of aluminium. So if I had 1,000 moles of aluminium, that means I'm only going to produce 500 moles of aluminium oxide. Whatever way you want to do it, it works out exactly the same. And you can do it for your simpler ratio as well. That means you need to do 1,000 divided by 2 and then multiply by 1. 1,000 divided by 2 is 500 moles. So for 1,000 moles of aluminium, I'm going to produce 500 moles of aluminium oxide. Now that I've brought that over, I can convert to mass. So mass is N times RFM. My number of moles is 500. My RFM of aluminium oxide, I can work that out off to the side. So the RFM is going to be 2 times by my mass of aluminium, which is 27, plus 3 times by my mass of oxygen, which is 16. That works out as 102. So 500 times by 102 is 51,000 grams. And I can simplify that down by converting it to kilograms. And I do that by dividing by 1,000, which is 51 kilograms. So once you've worked out the number of moles, you can bring it to anywhere in the equation, but you've got to remember your balancing number ratio. One final example to look at on page 19, and that's that if you're given the mass of a product, you can actually work backwards in your equation to get the mass of reactant that you would need to produce that mass of the particular product. The calculation is just done exactly the same way. Work out your number of moles and then bring it to the other side, part of the equation. So here we have got glucose being formed, or reacting with oxygen to form carbon dioxide and water. So same as always, let's write down the information we have underneath the equation. So it asks us to calculate the mass of glucose, and this is glucose here. So I'm going to put my question mark underneath glucose. Calculate the mass of glucose required to produce 432 grams of water. So I have 432 grams of water here. So I've written down the information that I have underneath the relevant part of the equation. And do that every single time to keep yourself right. The first thing I need to do, as always, is convert my mass of water into number of moles. So what I want to do, use my equation, N equals mass over RFM. My mass of water is 432 grams. And my RFM of water is 18. That works out as 24 moles, if you put it into your calculator. Okay, so now I've got my number of moles of water. I can bring it to anywhere in the equation. We're used to bringing it over to the products, but we actually need to work out the mass of glucose. So I can bring that over to my glucose. It doesn't matter that we're going from product to reactant. Okay, so we draw our arrow to show where we're moving from to where we're going to. But I need to consider my balancing number ratio. You can see that I have a balancing number of 6 in front of my water and a balancing number essentially of 1 in front of my glucose. So that means that for every 1 mole of glucose that we have, we form 6 moles of water. How I would normally write my ratio on the arrow is consistent with the balancing numbers ratios as to where they are. So you can see that my 6 is in front of my water and my 1 is in front of my glucose. So that's why I write my ratio as 1 to 6. However, since we're going from water to glucose, you could also consider that as a ratio of 6 to 1. Whatever way you would prefer to write it, we're going from 6 moles of water to 1 mole of glucose. So what we need to do is we need to divide by 6. So again, use your rule. You divide by the number you're going from and you multiply by the number you're going to. So we're dividing by 6 because that was the balancing number in front of our water. And we're timesing by 1 because that's the number in front of the glucose that we're going to. And think about it really, I should end up with a smaller number of moles because I have 6 moles of water and only 1 mole of glucose. So check that after you've done your balancing number ratio calculation. Think about whether it should be getting smaller or getting bigger. So 24 divided by 6 is 4 moles of water. So when I've produced 24 moles of water, that has come from 4 moles of glucose. Once I've got that, I need to convert to mass using my equation N times RFM. The RFM of glucose we need to calculate. I have 6 carbon atoms, so that's going to be 6 times by my mass of carbon, which is 12. I'm going to be adding that to 12 hydrogens, hydrogen with a mass of 1, and then 6 oxygens, so it's going to be 6 multiplied by 16. That gives me a total RFM of 180. So therefore my mass is 4 moles times by 180, which is 720 grams. So again, you can bring your number of moles to any part of the equation as long as you've converted it to moles. You cannot go from 432 grams to 720 grams. You have to convert to moles first. If you're still unsure about any of those calculations, go back and replay the examples and work through them again. But if you're confident, move on now to these reacting mass calculations. So take a new page in your blue books and take the title of Reacting Mass Calculations. And this is unit 1.7 if you add that to your title as well, so that you know which unit this is about. And answer the questions. Not just question 1 on this page, but over on page 20, finish off all of the examples of this type. So we're doing questions 1 to 6 on page 19, this page, and over on to the next page, page 20. So if you try those calculations now.